Hello everyone, my name is Xin Zhao from HKUST. Today I will introduce an efficient DiT-based action planner accelerator DiTPA. Recently, dual system VLA models are emerging as the mainstream paradigm for embodied robots, such as Physical Intelligence Pi0 and NVIDIA's N1. It connects two parts. Firstly, the task instruction and visual observation sent to the vision language model for semantic reasoning. Then the DiT model generates final actions. For the action planner, high action frequency is required for real-time interactions, such as 50 Hz for service robots and even up to 200 Hz for industrial applications. However, currently only 2.6 Hz is achieved on an NVIDIA A40 GPU, which results in a big gap compared to our actual demand more than 50 Hz. The limited speed mainly stems from three-level computation. At the trajectory level, each inference produces one action, and hundreds of inferences are required to complete a task. At the iteration level, multiple denoising steps are required to refine an action from random noise, typically 10 to 50 denoising steps. At the model level, multiple attention and FFM blocks are executed within each denoising step. Based on these limitations, we propose our co-design work DiTPA. This is the DiTPA software framework consisting of three strategies. First, to exploit the action redundancy, we propose an orientation-conditioned action prediction mechanism. We compare the orientation difference between consecutive actions. If the orientation remains consistent, the next inference is skipped and the current action is reused. Second, to exploit the denoising redundancy, we propose an alternating denoising with feature reuse method. For the next denoising step to be skipped, we will buffer current attention FFM features in advance. Then for the skipped step, the full computations are skipped. Third, to explore the multimodality redundancy, we propose an calibrated multimodal approximate computing scheme. The computations of redundant modalities are skipped, while the key features of redundant modalities are buffered to calibrate the attention computation. Here is the hardware architecture. The first feature is the action predictor, which can predict reusable actions at runtime. The second feature, reconfigurable PE array that can support matrix multiplication with changing token lengths. The next feature, multimodal scheduler, contains a data manager to control data buffering, reuse, update, and a sparse state controller to manage sparse data. Here is our evaluation. We select the mainstream liberal long task set as our workload. The hardware architecture is implemented at 28nm technology. As shown in the left side table, the power is only 1.05 watts. We also deploy the DiTPA to the real-world robotic arm system. For the accuracy evaluation, DiTPA's success rate is nearly identical to the baseline data. In the performance evaluation, DiTPA achieves an action frequency of 217 Hz on average. For the energy efficiency, DiTPA achieves an average 2,356 times improvement over the GPU. Compared to the existing DiT accelerators, DiTPA achieves energy efficiency improvement of more than 8 times and 11 times. For the trajectory sensitivity, maintaining orientation variation within a reasonable range enables both high success rate and speed up, as shown in the right side trajectory. When the threshold equals to 0 or 2 degrees, the robotic arm can successfully grasp the object in a single attempt and finally place the object at the right endpoint. Finally, to demonstrate DiTPA's scalability, we evaluate DiTPA on different manipulation benchmarks, such as carving and simpler aim, and more than 450 times speedup is achieved. Thanks for your attention. If you have any question, welcome to contact with us.